Hello there and welcome to class number 17. This is Monday, 15th of October 2012 and it's Coastal Processes Part 1. Now this class is split into 3 parts and these video lectures are therefore also in 3 parts. Part 1 is about waves, Part 2 is about beaches, and Part 3 is about barrier islands and lagoons. Right? But let's start with waves, because waves are basically what's shaping, if you will, the coastal environment. So let's look at the picture here first, and this is what we're talking about, right? We're talking about waves as they come in from the ocean. You can't really see them out in the ocean, and then at some point they become visible, they start to break, and then they wash up on the beach, causing erosion, right? And we're looking here at a shot of Point Reyes National Seashore in California, looking northwards along the California coast. So, waves. Alright, the big picture about waves is the water does not move. That's a little bit counterintuitive, so let me explain that to you. First of all, we need a definition. If you will, waves are rising and falling motions transmitted from one water molecule to the next one, right? We've all seen waves on rivers, waves on lakes, waves on oceans, right? So that's the definition. Now, waves carry energy, right? And as the wave travels, the wave transfers energy from one water molecule to another water molecule. Once the wave encounters something solid, for example, the coastline, the energy has to go somewhere. We can't destroy energy, we only can convert energy, right? And that gives us coastal erosion, right? So, wave carries energy. The water itself does not move horizontally, and that's a little bit counterintuitive, because when you look at the wave and you stand at the beach, it appears as though water is moving from the ocean towards you, but that actually is not the case. The water through which a wave passes through does not move horizontally. It moves up and down, as you can see in this animation here. Here's a water molecule, or imagine this being a wiffle ball, and the wave is traveling from left to right. But your wiffle ball or your water molecule is only going up and down. It's actually not moving horizontally with the direction that the wave travels. Therefore, waves transmit and move energy, but they do not move mass. That's a little bit strange. Let's look into that. Right? So, as each water molecule moves up and down as the wave travels by, that motion is transferred to the next one, to the next one, to the next one. But each individual water molecule does not actually move horizontally. Let's look at another example here. So here might be a wiffle ball, and here might be a bottle. And as the wave travels by, in this case from left to right, the water molecule goes up and down, the wiffle ball goes up and down, but it doesn't come to shore. In other words, when you're standing there at the beach looking out, and there's a wiffle ball, or there's a boat, or there's a basketball floating 200 yards offshore, that object will never make it to shore. Because as the waves travel by, it goes up, it goes down, but it will stay out there. The only way it gets eventually to shore is by wind. So waves transmit and move energy, but not mass. Therefore, waves technically do not have a velocity. Because in physics we define velocity by mass. But since there's no mass transport in a wave, the speed at which a wave travels is called celerity, not velocity. Kind of weird, but that's the way it is. So, final animations here, right? Here's your water molecule. We've looked at this now, right? Wave comes from left to right. Here's your wiffle ball. Here's your water molecule going up and down, but that wiffle ball, that water molecule will never make it to shore. Here's another animation, and then here's another one. Wave motion and wave period. Let's see what happens here. Here we got 2 people, and they have a string, and they create a wave, right? But what we really want to see is, imagine there's a ball on that string, and as they create a wave between them, that ball that's on that string goes up and down, but that ball will never reach it from this guy, will never make it from this guy to the woman over there, right? Because once again, there is no horizontal movement involved in a wave. So, waves are created by wind, right? And basically, as the wind blows across the ocean or across the water surface, it creates tiny, tiny eddies, little micro ripples. Therefore, the surface of the water gets a little bit rougher, the wind has better grip, now the wind becomes turbulent, and now energy is being transferred from the wind to the water surface, and you get bigger waves. Stronger winds are more turbulent, and you get easier and bigger waves out of that. So a wave that you see on the surface of the ocean, a wave that you see on the on a lake is basically created by wind. So here's a map of the Earth, right? We see Australia here, Africa, South America, and the color coding denotes sort of the average wave height. And as you can see, the largest waves you can find here in this part of the globe, south of the Indian Ocean, right? Sort of around the continent of Antarctica. Why is that? Because there is the largest part of the ocean where there's no interruption by continents or by islands. It has the largest fetch. Wind speeds are consistently high, and they blow in a constant direction. Therefore, you get the highest waves. Smallest waves on the planet you can find where you have a lot of islands around the equator, right? Where you don't have a lot of fetch, as we call it, because the wind is constantly interrupted by islands. So, for example, in the Caribbean here, right, Southeast Asia, right, that's where you have the smallest waves on the planet. Now, what's interesting about waves is that when they are in deep water, right, your water molecule can oscillate freely. It can go up and go down. But as soon, and you can see that here on this photograph, as soon as the waves get closer and closer to shore, where the water depth gets shallower and shallower, your oscillations begin to hit the bottom, and your waves start to steepen and your waves start to break. Let's look into that in some detail here, right? So here we have a wave coming in from the left, and it's in deep water out here. Your water can go up, you can go down, can go up, can go down, no problem. But as the water depth decreases as you approach the shore, at some point, your wave will begin to feel the bottom of the ocean, right? So your water molecule, the free motion of your water molecule is now constricted by the ocean floor. At that point, the celerity of the wave slows down, the wave height increases, and it starts to break. Right? So that's why when you look out from the beach, within a certain distance of the beach, the waves start to break and start to get bigger. It's because they get influenced by the slowly shallowing of the water depth. So here's an example, right? Out here, it's deep enough, right? The rising and falling motion of your water molecule is not impacted by the ocean floor. Right around here, it becomes shallow enough where now, if you will, the molecules bump into the ocean floor. They don't really bump into the ocean floor, but they begin to get influenced by the ocean floor. They begin to feel the ocean floor. The celerity slows down, your wave gets slower, your wave gets taller, right? And then eventually the surf zone starts breaking. And also the wavelength gets shorter. So, here's a nice example. Here we have a wave that's just about to break and is already breaking here. And that's probably because of water depth. Most likely, the water depth here is a little bit less than here. It's a little bit deeper here, right? So, here we already have a breaking wave, and here the wave is just about to break. Another cool picture here, right? We're south of San Francisco, near Pacifica, right? And we have the waves coming in here from the right, from the Pacific Ocean, right? They begin to feel the bottom, and they're already breaking. You can see that the wave length is approximately similar. The distances between wave the breaking waves here is approximately the same. Now, let's look at this as an animation. Right, so we have a wave coming in from the left. And here's our beach, if you will. Here's our wash and backwash zone. And out here, right, it's deep enough. Your water molecules go up and down, and they don't really feel the ocean bottom. But you know, as the wave approaches the shoreline, right around here, that's where it gets shallow enough so that the motion of your water molecule is impacted by the ocean floor. And as you can see, first of all, the speed of the wave decreases, your wave height increases, right, and it begins to lean forward and eventually tip over, if you will, and breaks in the surf zone. So that's what happens to waves when they go from the ocean to the beach, if you will. Now, a quick word about tsunamis. Now, tsunamis are ocean waves that are triggered usually by underwater earthquakes. So they're not tidal waves, right? They're always called like, ooh, tidal waves, but they're not. They're triggered by earthquakes. They're not triggered by tides. And tsunamis are tricky because they are very difficult to see, very difficult to spot out in the open ocean because their wave height is relatively small, but they have enormous wavelength. So the problem is when they approach the continental shelf here, when water depth decreases, then their wave height increases dramatically up to maybe 100 feet and more, and you get major devastation in coastal areas. Tsunamis are a real natural hazard. This is the 2004 Indian Ocean earthquake and resultant tsunami. This was just after Christmas in 2004. Over 300,000 people died. Right, so there was an earthquake here off Indonesia that triggered a tsunami, and a lot of parts there just got completely obliterated. And in the next slide, we're going to see an animation of that earthquake and then the resulting tsunami traveling over the Indian Ocean. So let's go next, and here's our tsunami traveling across, crowding across the Indian Ocean, hitting Thailand, hitting India, hitting Sri Lanka, and then even influencing the east coast of Africa. Let's go back and watch this again. Oh, there it's replaying itself actually. Right. So earthquake here triggering the tsunami just traveling through the Indian Ocean. Over 300,000 people dead. A few examples of what happened here. This is Sumatra, right? Here's the picture before the tsunami came through, and then basically the entire city center of that town completely destroyed. Right? Apparently, wave height more than 50 feet when it hit. Here's another example. Now we're looking at Thailand. Here's the coastline of Thailand. Here, green, beautiful, lush vegetation. This was about in 2002. And then here, right after the tsunami came through, all these gray areas is where the vegetation has been basically ripped out of the ground and stripped away by the tsunami. More recently, we had the earthquake and resultant tsunami here in March 2011 in Japan, right? We've all seen these incredible pictures of the tsunami basically just like coming on land and absolutely destroying everything in sight. And that, of course, also triggered the explosions at the Fukushima nuclear power plant. Tsunamis are a real problem, are a real natural hazard. That's why we have a very sophisticated tsunami warning system in the Pacific Ocean, right? In order to sort of protect, if you will, coastal areas. And here's an interesting thing. You see travel times here. So if you have a tsunami, for example, if you have a big earthquake, say in Hawaii, and the tsunami is triggered, it'll take 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. About 5 hours to reach California, right? About 8 or 9 hours to reach California, and then more than 12 hours or so to reach South America. But those times are pretty short. If you think about evacuating a large area such as San Francisco, such as Los Angeles, in less than 5 hours, it's a rather tricky business. And that assumes, of course, that the tsunami is immediately detected and warnings are issued immediately. So earthquakes in the Pacific Ocean area are a problem, and we've seen that, of course, demonstrated in Japan there most recently. So coastal environments in general, very dynamic places, very vulnerable to natural disasters, very vulnerable to climate change, because sea level rise, and then also very beautiful and appealing to live in. And that might be the bigger problem is, if you think about sort of two intersecting circles, you have maybe here the intersecting the circle here might be natural events such as hurricanes, floods, earthquakes, tsunamis. But then of course we have population, right? And more and more people live or tend to live closer and closer to the ocean, right? So the potential for natural hazard to become a natural disaster is getting greater and greater and greater. And then also think about how much wealth and how much infrastructure is concentrated in the coastal areas, right? So this is Cape Cod. So when you're on Cape Cod next time, think about that. You're in an incredibly beautiful environment, but you're also in a very dynamic environment, and therefore in an environment relatively vulnerable to all kinds of impacts, both from natural occurrences, but also from climate change. So this was part one, waves, right? And in part two, we're going to look at beaches and how waves interact with beaches. So I'll see you back in part two. Thank you.